Hi everyone, thank you for joining us again. In this session in maths, we are going to be looking at functions and inverses. Now it is a section that some learners do get confused about. So what we aim to do today is to try and unpack the section a little bit so that you are a little less confused when you are confronted with this type of question in an exam. So let's go straight into it. What exactly is an inverse? Well, you can think about an inverse function as a function that does the reverse of the original function. So say, for example, we have f of x is equal to x plus 4. That's the original function that's given to you. And if I wanted to find out an output value, I could obviously put in any input value for x. Say I put in 3 for x, I would get 3 plus 4, f of x is equal to 7. So my output value is 7. Now what the inverse function does is you start with an input value of 7 and you end up with a 3. You can check this, but the inverse of the function f of x is equal to x plus 4 is the inverse function x minus 4. And see what happens if I now take what used to be the output of f of x and I put it into the inverse function, f inverse of x. So I put that 7 in as the input value. I get 7 minus 4, and my output is now 3. So do you see what has happened? The input value became the output value, and the output value became the input value when we reversed the function. So in other words, when we found the inverse of the function x plus 4. Now there's some important notation and terminology that you guys need to be familiar with. Let's have a look at this. We say that if a function is a one-to-one relation, and remember this is where you use the vertical line test and you test what kind of relation your function has. So if a function is one-to-one, then its inverse will also be a function, okay? We can represent the inverse using inverse function notation. Now, we're going to talk a little bit more about a one-to-one relation and an inverse function in a little bit. But let's just talk about the notation. So I haven't forgotten about this key concept. We will come back to it. If the function is given as f of x, then you'll notice that the inverse function is written as f inverse of x. Please do not make this mistake. This minus 1 is not a power. It is not an exponent. So it might look like it's a power, but it isn't. So guys, you cannot say f to the power negative 1 of x or f exponent negative 1 of x. f to negative 1x, anything like that is incorrect terminology. And what you're referring to when you're saying f to the negative 1 of x is actually a completely different function. It isn't the inverse function. So please note that even though the minus 1 looks like an exponent, it isn't. So do not confuse the inverse function, f inverse of x, that's how you say it. So do not confuse that with the reciprocal of a function. So say I had, so here we're just going to do a quick example. Say I have an original function of y is, or you're given f of x is equal to a half x, okay? You can test this for yourself. The inverse function of y is equal to a half x would be the function 2x. So f inverse of x would be 2x. However, f of x to the power of negative 1 is the reciprocal function. So that would then be the function 1 over, and in fact this is incorrect here, it's going to be the function 1 over f of x. Okay, so 1 over a half times x, and that will give you the function 2 over x. Okay, so therefore the reciprocal function when we're referring to f of x to the power of negative 1 is 2 over x. And you can see that that function is clearly different. It's got a completely different notation to f inverse of x, which is 2x. Okay, make sure you understand that concept quite clearly. So how do we find the inverse then? Well, you simply swap the x and the y values of the original function, and then you once again make y the subject of the formula, or we say you solve for y. So say for example we had y is equal to 3x plus 4 and I want to find the inverse. Remember, y is just another notation for your functional notation. Y could be f of x or g of x or h of x or whatever variable we chose there. So f of x is the same as y. Do not get confused with that. Okay, so the first thing we do is we swap the x and the y value. So I'm going to swap x with y. So I now get, instead of y equal to 3x plus 4, I get x is equal to 3y plus 4. And the next step is to make y the subject. So I'm simply now going to isolate the y, right? So I'm going to take 4 over to the left-hand side. So I get x minus 4 is equal to 3y. And then I divide both sides by 3 to get my inverse function. So y is equal to x minus 4 over 3 would be the inverse function. You can simplify this to a third x minus 4 over 3. Once you've found the inverse function, sometimes we might say write it in functional notation. Then you won't write y here. You will say f inverse of x is equal to a third x minus 4 over 3. All right. So it's quite a simple procedure in order to find the function. Swap x and y and then make y the subject of the formula. So are all inverses functions? So let's think about this. Now, we spoke about one-to-one functions giving us inverse functions. Let's talk about this a little bit now. If the inverse of a function is also a function, then that function is said to be invertible. Okay, so if the inverse of a function is also a function, that function is said to be invertible. So for example, when we looked at this one with the straight line, y is equal to 3x plus 4, that was a function, that's a straight line. Then, and its inverse, which was a third x minus 4 over 3, that was also a function. So therefore, that is said to be an invertible function. All right, it's just terminology. It's not a key thing for your exams, but it's nice to know when a function is invertible. Only one-to-one functions are invertible. So we looked at a straight line, which is a one-to-one function. One-to-one, remember, means for every single x value, there's a single y value. So for every input, there's a single output. So a single input, a single output. That's what one-to-one means. Now, does that mean I can't find inverses of other functions? No. You can find the inverse of other functions. However, it might be the case that the inverse graph is not a function. Okay, we're going to have a look at an example of this. So we say often the inverse of a function is not a function. And in that case, what we then do is we restrict the domain to make the inverse a function. So say, for example, our original function is f of x is equal to x squared. Now, if I draw a quick rough sketch, it's going to look like that. This is f of x is equal to x squared. And if I were to find the inverse of this, I'm going to get a graph that is not a function. I'm not going to show you that picture straight away. We're going to get there. But how can I tell that the inverse of this graph, just by looking at it, is not going to be a function? Remember, we said only one-to-one functions will have inverses that are functions. If you did a vertical line test on this parabola, you will see that this is not a one-to-one function. This is a many-to-one function. So I have many x values going to the same y value. So this is a many-to-one function. So when you invert it, you're going to get a graph that's going to become a one-to-many relation, and therefore it is not a function, but we'll talk about that just now. So let's just have a look at what our equation would be. F of x is equal to x squared. What's the equation of the inverse? We swap x and y, so remember f of x I can write as y. So I'm going to get x is equal to y squared, and then I solve for y. So I solve for y by square rooting. Remember, whenever you take the square root, it's plus or minus. So therefore, y is equal to plus or minus the square root of x is the inverse of f of x is equal to x squared. Now, remember that the graphs of f of x and f inverse of x, which is the inverse, they are symmetrical about the line y is equal to x. So what that means is each point, and we're going to have a look at this, I've already found the equation, each point along those two graphs, f of x and f inverse of x, the x and y values swap around because y is equal to x. So this y is equal to x, we call it the axis of symmetry. All right, so therefore, if you have a look at the screen, I've now drawn for you what f of x is equal to x squared looks like. So our original function f of x is equal to x squared is drawn. This line y is equal to x goes straight through the origin, all right, and it looks something like that. Obviously, mine is not drawn perfectly because I don't have a ruler there. So y is equal to x would be the line that reflects the x and y values. So if you look at the inverse graph, which is drawn as y is equal to plus or minus the square root of x, you will see, let's take any x value, say let's look at the point minus 2, 4 on the original function f of x. You'll see that point reflected in that line y is equal to x. You see the x and the y values swap. So instead of having x is minus 2, y is 4, we have x is 4, y is minus 2, and you can test it with many other values on these two functions. Now, we were talking about the fact that this inverse graph is not going to be a function. You can see it straight away. It's turned on its side, facing all the positive x values. So therefore, if we did a vertical line test, it would cut it at more than one point. So therefore, the inverse graph of this parabola f of x is equal to x squared, the inverse is not a function. We can restrict the domain, however, of the original function so that the inverse becomes a function. And what we're going to do, guys, is I want you to think about how you can restrict the domain. When we come back after this quick break, we will then talk about how we can restrict the domain on that original function to make sure the inverse function is a function as well. We're back after this. Hi everyone, welcome back. So before the break, we were talking about how we can restrict the domain of the original function f of x, being a quadratic function or a parabola, in order to make sure that its inverse is also a function. So how do we do that? Did you think about how we could do that? Well, there's two ways we could restrict that domain. So we can either restrict the domain of f of x to x is less than equal to 0, or x is greater than equal to 0 to ensure that its inverse is also a function. We're going to have a look at that in a second. The one thing that's important to note as well is that the domain of the original function becomes the range of the inverse and vice versa. So have a look at our original function f of x is equal to x squared. You will see that there the range is all the y values greater than or equal to 0. So y is greater than equal to 0 is the range of f of x. Now the domain of f inverse of x, which is the graph that's turned on its side, which is y is equal to plus or minus the square root of x. The domain now, if you look at that graph that I'm just going to highlight there, is all x values are now positive. So therefore, the domain is now x is greater than equal to 0. All right? So you can see that the range became the domain. Similarly, if you looked at the domain of the original function f of x, which is x is an element of real numbers. There's no restriction on our x values in f of x is equal to x squared. You will now see that there's no restriction on your y values. They can be going up to positive infinity, down to negative infinity. So therefore, y is an element of real numbers is now the range of the inverse graph. So you can see that the domain of the original function became the range of the inverse function. So that's just something to note. So how do we restrict it? We said either we're going to say x is less than equal to 0 or x is greater than equal to 0. So if we take the negative part of f of x, so I'm just restricting to x is less than equal to 0. So it's all the negative arm of the graph. So I just want a single arm on this graph so that when I reflect it in the line y is equal to x, we will get a graph, right? Do you see the one that's drawn there? The inverse graph is now just the negative values of the square root of x. And if I did a vertical line test on this inverse function, you can see the vertical line will only cut it at one point, and therefore the inverse function is now a function. So by restricting the original domain to x is less than equal to 0, which means that the range of your inverse graph will now become y is less than equal to 0. Do you see that by restricting the domain, we now get an inverse arm of f of x that is a function? Similarly, we could have restricted the domain to x is greater than equal to 0, in which case we would get this inverse function here. Okay, and you can see I'm saying an inverse function, not an inverse graph. This inverse is now a function. If we draw a straight line through the graph, you will see that it cuts the graph at only one point. So now by restricting the domain, we have restricted the range to y is only positive values, and therefore the inverse is now a function. Okay, so importantly, remember, until we've restricted that domain, we cannot call the inverse a function. And hopefully I haven't made that mistake anywhere and you were listening very carefully. Until we've restricted the domain, we cannot call the inverse of this graph a function. We just call it y. We can only use functional notation with the inverse graph once we've confirmed that the inverse graph is indeed a function. So now we can certainly put in f inverse of x. Before we just had y is equal to plus or minus the square root of x. All right, guys, hopefully that is all very clear to you. One of the big things you learn in grade 12 when you deal with inverses is something called the log graph. And the log graph is the inverse graph of the exponential graph. And remember, when you're thinking about logs and exponents, they always are related because a log is just another way to write an exponent. So it makes sense that since they were related when we were looking at the algebra of exponents and logs, it makes sense that they would be related when you deal with functions as well. An exponential graph is a one-to-one function. Therefore, it must be invertible, which means that the log graph will also be a function, a one-to-one function. All right. So say we had the exponential function f of x is equal to a to the power of x. That would then have an inverse function f inverse of x is equal to log x base a. How did we get there? Okay, so we started off with y is equal to a to the power of x. To find the inverse, I swap the x and the y values, so I get x is equal to a to the power of y. I now cannot get to the value of y without using logs, and this is why you do a brief section on logs in grade 12. It shows you a different way to write this exponent y. How do we write it? We write it using logs. So y, which is the exponent, I can write it as log of the number to the base of a. Remember, the base of the exponent should always become the base of the log as well. So therefore, the inverse function of a to the power of x is log x base a. Again, these graphs are symmetrical about the line y is equal to x. So that means you swap your x and your y values, which makes it quite easy when you're sketching these graphs. All right. Let's look at an example. Say I have y is equal to 3 to the x and I want to find the inverse of this graph. What do? I swap the x and the y values. So I get x is equal to 3 to the power of y. I then need to solve for y, which in this case, because it's an exponent, I have to use logs. So I rewrite the exponent y using logs. So if you think of it that way, guys, now that I just want to mention this, if you think about a log as a different way to write an exponent, you will never get confused about how to rewrite your exponential equation in terms of logs, because the exponent is what you want to rewrite. So the exponent will be what you will write on either the left or the right hand side, and then it's just the number and the base that you've got to think about. So y is going to be equal to log x base 3. That will be the inverse of y is equal to 3 to the x. Some other things when I think about this graph, y is equal to 3 to the x. It is an increasing exponential function. How do I know that? Because this base here is greater than 1. So if a is greater than 1, you will have an increasing exponential function. What that means is as your x values increase, your y values increase as well. All right? So therefore, we can see that when we draw the graph, we will have an increasing exponential graph. So therefore, our log graph will also be an increasing function. What exactly is it going to look like? We're going to see just now. Remember that when you draw your exponential function, you have a y-intercept of 1. And because we're thinking about inverses, we start thinking, well, if I reflect in the line y is equal to x, that must mean that my x-intercept is now going to be 1. Because remember, with inverses, your x's and your y's swap around. Your domain and your range, they swap around. So therefore, if the y-intercept was 1 on the exponential function, that means the x-intercept is now going to become 1 on the log graph. Okay? How exactly is this graph going to look? We'll have a look here. You see that y is equal to 3 to the x. We've got, and you see I'm saying 3 to the power of x or 3 to the x. But when we use inverse function notation, we cannot call, remember, I'm just going to remind you again, we cannot say that that's to the power of -1. All right, let's go back there. So let's just get back to our thought here. So we've got that the exponential function has a y-intercept of 1. So therefore, the x-intercept of the log graph is now going to be 1. If I take any point on the exponential function, and once you know the general pattern of the graph, you only need 1 or 2 points in order to sketch the curve. So if I take a point x is equal to 1, substitute x is equal to 1 in there, and I get y is equal to 3, I can then plot the inverse of that, so the reverse of that, where x is 3 and y is equal to 1, and that will be a point on the inverse function, which here we've written as x2 is equal to 3 to the y, but remember it's log base 3 of x. Okay, it's the same thing. All right, so therefore we can see that the log graph is an increasing function. As x is increasing, y is increasing. Okay, we also see that we have that the domain of the original function becomes the range of the inverse function. So what was the domain of the exponential graph? Well, the domain, we saw that x could be almost anything it wanted. It just couldn't ever touch. We couldn't go here. Okay. So we had no x-intercept. So what that means is the y-axis was an asymptote. Sorry, I'm saying that wrong. The x-axis was an asymptote to the exponential function, okay? The exponential function could not cut the x-axis, so the x-axis was an asymptote. Now, in the log graph, the opposite is going to happen. It's going to be the y-axis that is going to become an asymptote to that function, okay? So therefore, we're going to have that x cannot be equal to 0 in the log graph, because in the original function, y could not be equal to 0. So it swaps around. All right. All right, guys. I want to quickly just explain a little bit more before we go on to a decreasing exponential function. Let's just see what we have time to do here. Other things that are special about these graphs and that we need to remember. So we swap some points around. We can see if we have the point 1, 3, it becomes 3, 1. And you can certainly play around with some negative values as well. So take x as -1 and a third, and then you will get a third and -1 on the log graph. Let's talk a little bit more about the shapes of the graphs. We can see that they are both increasing functions, and when we think about an exponential function and a log function, we've got to remember that whatever the exponential function is doing, the log function will do. So we don't really have time to go over the decreasing exponential function, but remember, because the function, the exponential function is decreasing, so that means it will have a fractional base so we'll have like y is equal to 1/2 to the power of x. So because of that fractional base, that will be a decreasing function, and therefore the log graph will also be a decreasing function. Okay, I'm talking way too much. It is time for us to say goodbye for this segment. We will see you again next time. Cheers.